In this video, we will look for the trace of a matrix. So, trace of a matrix is an important concept defined only for a square matrix. Okay, so it is actually the sum of the elements present on the main diagonal of the matrix, and the diagonal runs from the top left corner to the bottom right corner. Alright. Now, after looking into the trace of the matrix, we'll continue our discussions on types of matrix. So there are various other important types of matrix which are commonly used in mathematics, which we did not continue then because we needed to introduce some more basic matrix operations. So we will again continue with the types of matrix in this video after discussing trace of matrix. Alright. Now, as already said, trace of a matrix is the sum of its diagonal elements. So, trace is equals to sum of its diagonal elements. So, we write trace of a matrix as this, like this, TR of a matrix A in bracket. So, trace of matrix A, so let us define A as 1, 2, 3, 4, 5, 6, 7, 8, 9. So, trace of A would be sum of its diagonal elements, that is 1 plus 5 plus 9, that is equal to 15. So, this is the trace of a matrix. Alright. Now, let us look into some of the properties of trace. So, property number 1 says that trace of A plus B will be equal to trace of A plus trace of B. Okay. Property number 2 says that trace of AB can never be equal to trace of A into trace of B. But property number 3 says that trace of AB will be equal to trace of BA. Alright. Coming to the next property, property number 4 says that trace of A, B, C, D is equals to trace of B, C, D, A is equal to trace of C, D, A, B is equal to trace of D, A, B, C. So basically what it says is for cyclic rotation the trace remains same. Alright. Cyclically we are omitting one matrix and putting it to the other side of the product. Right. Now let us continue our discussion on types of matrix. So continuing with the last types of matrix. Let us start off with symmetric matrix. So what is a symmetric matrix? It is a square matrix whose transpose is equal to itself. That is, if you change the rows and columns of a matrix, if you change the rows into columns of a matrix, the matrix remains identical. There's no change in it. Let us give an example. Alright. So consider matrix 1, 2, 3, 4, 5, 6, 2, 3, 6. Alright. So let us consider this to be A. Now what we need to do? We need to find out A transpose, right? What is transpose? Transpose is changing rows into columns and columns into rows. So changing the first column into row. 1, 2, 3. Changing the second column into row. 2, 4, 6. Finally, changing the third column into row. 3, 6, 5. So what we can make out is 1, 2, 3, 2, 4, 6 and 3, 6, 5 is identical with A. So basically A transpose is coming out to be equal to A, which is equal to A. So this is what we wanted, right? For a matrix to be symmetric, we defined it to be as A transpose is equal to A, and this is what is coming. So we can make out a simple analogy from this. The analogy being that if these are the diagonal elements, okay. So look, both all the elements on both sides of the diagonal are symmetric. 2, 2, 2, 3, 3, 6, 6. Alright. So apart from the diagonal, both sides of the diagonal needs to be symmetric in order to be a matrix to be symmetric. Alright. Coming to the second type of matrix, which is called skew symmetric matrix. Alright. So what is the definition of skew symmetric matrix? A transpose comes out to be minus A. Alright. For normal symmetric matrix, it was A transpose was coming out to be A. For skew symmetric matrix, A transpose comes out to be minus A. Let us take an example. Let us consider A to be 0, 1, 2, 3, 0, 0, minus 1, minus 2, minus 3. Alright. Now A transpose will become nothing but change the rows into column and columns into row. So this comes out to be 0, 1, 2, minus 1, 0, 3 and minus 2, minus 3, 0. So we can see that this is nothing but minus A. Look, this was A and this was A and this is A transpose. So what we can see is if we multiply minus with A, it becomes identical with A transpose, right? So what we have done is we have done nothing but change the rows into columns and columns into rows. So what we can make out is that for a skew symmetric matrix, it is important that the diagonal elements become 0 and both sides of the diagonal elements, all the elements on both sides of the diagonal are symmetric, but one being the negative of the other. So if this is 1, this has to be minus 1. If this is 2, this has to be minus 2. If this is 3, this has to be minus 3. Alright, and the diagonal element being 1, 0, 0, 0. Alright, so this is what I meant to say. Now here is another important statement about symmetric and skew-symmetric matrix. Any square matrix can be converted into symmetric or antisymmetric matrix. Okay, so all matrix need not always necessarily be symmetric or skew-symmetric, but there must be some symmetry in every matrix. That is, we must be able to make symmetric or antisymmetric matrix out of the given matrix. So any square matrix can be converted into a symmetric part and an antisymmetric part. And how can we express that in terms of statement? The statement is A, which is a matrix, can be written as a symmetric part, half of A plus A transpose, and an antisymmetric part, which is half of A minus A transpose. Alright, so this is the symmetric part and this is the antisymmetric part. Alright, so A, which is a matrix, can be converted into a symmetric part and an antisymmetric part by simply adding transpose with itself and subtracting transpose with itself and dividing it by 2. Alright,